The 600-meter circumference building is Diamond Light Source, the UK's national synchrotron facility. Diamond Light Source produces extremely bright light that is harvested from electrons, which have been accelerated close to the speed of light and travel around the so-called storage ring. As the electrons travel around the storage ring, they emit the synchrotron light that is channeled into the beamlines, where it is used for a wide range of microscopy applications. The brightness of the light, and hence the quality of the experiments in the beamlines, is reduced if the electrons exhibit strong vibrations. The vibrations are induced by external disturbances, such as people walking around the building or cars passing by on the nearby motorway. To suppress these vibrations, hundreds of magnets and sensors are combined into a feedback loop, the fast orbit feedback. At Diamond, the feedback is operated at 10 kHz, meaning that the magnet set points are updated 100,000 times per second. The fast orbit feedback reduces the trajectory error of the electrons down to a few nanometers. My name is Kempf, and as part of my DPhil at the control group of the University of Oxford, I am working with Diamond Light Source to design and implement new controllers for the imminent next generation upgrade, Diamond 2. Diamond 2 will increase the brightness of the synchrotron light, but also increase the dimensions and performance requirements of the fast orbit feedback system. Existing fast orbit feedback controllers effectively attenuate disturbances up to 200 Hz, but Diamond 2 will require a bandwidth higher than 1 kHz. This and other changes prohibit Diamond to reuse their current controller. In the past years, I have developed new controllers for Diamond 2, and I also integrated the Diamond 2 hardware into the existing storage ring, which allows me to test new algorithms on the real machine. One controller we are evaluating is Linear Model Predictive Control, or short MPC, which finds a sequence of control inputs, UK0 to UKn-1, that minimizes a quadratic function over horizon n, or it is assumed that the input is restricted to some polyhedral set. Here, a more compact form of MPC is shown, where the state space equations have been substituted, and the state space matrices are now incorporated in the Hessian J, as well as in the objective function vector q. Note that q depends linearly on the state estimate x hat and the set point variables, which are all obtained from an observer. At every time step, the present optimization problem is solved, and the first input of the sequence, UK0, is applied to the plant. After receiving the new measurements, the observer is updated, and the optimization problem solved again. One of the main advantages of MPC is that it is possible to restrict inputs to a certain constraint set, and Diamond 2 will require a controller that can consider amplitude and slew rate constraints. Let U be the input at time k and V the input at time k-1, then the set on the left models a constraint set of an input with amplitude and slew rate limited by alpha and rho, respectively, and this is also visualized on the right. The constraint set of our MPC problem is then obtained from concatenating these sets at each horizon stage. In addition to the presence of input constraints, fast orbit feedback systems face three main challenges: speed and size, which are aggravated by the strong directionality of the system. Most synchrotrons, including Diamond 1 and 2, are such that some outputs are very hard to control, whereas some outputs are very easy to control. This talk addresses the strong directionality of the synchrotron, which in our case manifests itself in the Hessian of the MPC problem, here defined for horizon 1 and 2. The matrices A and B come from the state space model. The matrices Q and R are state and input weighting matrices, and Q is chosen as C transpose C, where C is the measurement matrix from the state space system. The matrix P is the terminal cost matrix of the MPC problem. Because of the strong directionality, the matrix C is ill-conditioned and therefore also Q. A standard way to choose P is to obtain it from the discrete time algebraic Riccati equation of the corresponding infinite linear quadratic regulator problem. If Q is ill-conditioned through the matrix C, then it can be shown that for reasonable choices of R, the matrix P is ill-conditioned. It then follows that the Hessian, being proportional to P, is ill-conditioned as well. For larger horizon, the condition number of J becomes even larger. An ill-conditioned Hessian is problematic for several reasons in practice. On one hand, it introduces numerical errors and sometimes requires to implement the controller with a higher numerical precision. On the other, it also affects convergence properties of the solver, and in our case, we are using a version of the fast gradient method which is known to show particularly bad convergence properties for ill-conditioned Hessians. However, the fast gradient method suits a high-speed parallel implementation very well, and it consists of three main steps. The gradient step, which is a matrix vector multiplication, the projection onto the constraint set, which in our case is explicitly known, and the beta update step, a vector addition. Here, the steps are repeated for a fixed number of iterations. And this number is mainly determined by the available computation time of the controller, which must be less than 100 microseconds for diamond 1, or with our hardware, roughly 133,000 processor cycles. If the condition number of the Hessian is large, then the fast gradient method will require a large number of iterations to achieve a predefined level of suboptimality. In simple cases, the Hessian can be preconditioned by methods such as diagonal scaling. But with our heavily ill-conditioned measurement matrix C, which results in an ill-conditioned terminal cost matrix P, this method does not work. Here, we propose to condition the terminal cost matrix P instead, which can be done by modifying the following semi-definite program. This SDP returns the same solution as the Riccati equation, which has been reformulated using the Schur complement to obtain the given linear matrix inequality. By adding the last two lines, the condition number of the Hessian is limited to kappa max. And the condition number constraint can be reformulated as an LMI for a symmetric and positive definite matrix such as J. If it has a solution, this SDP returns a matrix P that has a limited condition number and is closest to the Riccati equation solution. I have solved this SDP for the beam stabilization problem, and the results are as follows. The figure shows the average number of iterations required to solve the MPC problem up to a predefined level of suboptimality. With the Riccati equation solution, the condition number of the Hessian is approximately 3000, and the fast gradient method on average requires 200 iterations for horizon 1 and 300 iterations for horizon 2. Not that it would be technically impossible to implement that many iterations at the required rate of 10 kHz. Using the proposed method, the required number of iterations can be controlled. Here, the figure shows the number of iterations for a maximum condition number equal to 10, 20, and 50. It can be seen how the number of iterations drops below 50, which is feasible for our practical implementation. Note that the optimization problem can be infeasible for a significantly small condition number, and note that for decreasing condition numbers, the performance of the MPC can also decrease, which is visualized in the following plot. The figure shows the so-called integral beam motion, which is a standard performance measure for orbit feedback systems. The integral beam motion, in essence, is the integral of the absolute value of the output sensitivity, and it represents a measure for the worst-case disturbance attenuation. The controller performs best if the terminal cost matrix is obtained from the Riccati equation, and it performs worst if the condition number is limited to 10. It can also be seen that the difference is more pronounced for horizon 2, which is a natural consequence of the structure of the Hessian. In summary, we are trading off convergence speed of the solver versus performance of the controller. To test the MPC algorithm on diamond 1, we decided to use kappa max equal to 20 and parallelize the fast gradient method, including observer, onto the 8 cores of a Texas Instruments C6678 digital signal processor clocked at 1.4 GHz. The Execution times are shown here for Horizon 1 and 2. For Horizon 1, and using 20 fast gradient method iterations, the magnet set points are produced at a rate of 14.4 kilohertz, or 69 microseconds. But for Horizon equal to 2, we require more than 200 microseconds, which is far beyond the allowed execution time of 100 microseconds. For Horizon 2, the algorithm could be implemented on an FPGA. For Horizon 1, updating the observer, the objective function vector, and the constraint set requires roughly a third of the computation time, which is not negligible. We successfully ran the MPC algorithm on Diamond 1 under low current operating conditions, and we are currently preparing experiments that will evaluate MPC under normal operating conditions. This will allow us to compare MPC with existing controllers. With that said, I arrive at the end of my talk. In this presentation, we investigated the feasibility of the MPC for the fast orbit feedback system of Diamond light source. We focused on the solver convergence, which is heavily affected by the measurement matrix. We proposed an alternative to diagonal scaling of the Hessian. In our alternative method, the condition number of the terminal cost matrix is reduced using an SDP that combines the Riccati equation and the condition number constraint. We have seen how, in our case, a small condition number increases the convergence speed, but also decreases the controller performance. My name is Kempf, and I thank you very much for watching this video.